Okay, so today's webinar is about nuclear batteries or atomic batteries. Okay, so yeah, so and we all know that an atom is the smallest constituent unit of ordinary matter that constitutes a chemical element, and every solid, liquid, gas, and plasma are composed of neutral or ionized atoms. Now, atoms are extremely small. Okay. Now, atoms are extremely small and typically around 100 picometers across. So, inside an atom, there is a nucleus. So, smashing the teeny subatomic nucleus generates immense amounts of energy. Now, in terms of physics, so the highest possible form of energy, we all know that E equals mc square. So, where m is the mass and c is the speed of light. Yeah. Now, nuclear energy yeah. Now, nuclear energy is being developed for various applications. Now, one of them is for generating power for basic user needs. Like we all use nuclear energy power. For high amounts of power, we use a or we need a nuclear reactor. Okay, so we need a nuclear reactor. But for intermediate or like small amounts of power, like for 100 or 10 or 100 kilowatts of power, so the nuclear reactors are not feasible enough. So here we need a small size power generating source, and these are called nuclear batteries or atomic batteries, or they are known as nuclear generators or whatever like we may want to call. Okay. Now, these nuclear batteries are small in size, generates a good amount of power, portable to use, and not like dangerous as the big and powerful nuclear reactors. Now, coming to the nuclear energy was like first termed in the 1900s. So the term nuclear energy and the research already started in 1900s. So later in 1913, so Henry J.G. Moseley, he termed the or he coined the term the beta cell, and he developed a beta cell. So beta cell basically use the beta particles or the beta rays, whatever you say. And after that, there are several research experiments, developments, and innovations and evolutions happened. And later on, Paul Brown developed a radioisotope electric power system which used strontium 90. And later on, he used it. Later on, he used in 1945. He used the radium 226. Okay. Now, these elements or these devices are very small. So they are like a grapefruit sized device. So the radioisotope thermoelectric generator or the RTG commonly called, it basically in 1950s, it used the plutonium 238. So later on from 1950s, the nuclear batteries or nuclear generators were used for space applications. And then in 1954, so the Radio Corporation of America, it developed small radio receivers and hearing aids. And later on in 1959, the nuclear battery was actually patented. So before that, no patent was done. But in 1959, so the first battery was patented by Tritium Labs. So in now from after that in 1960s, it was mainly used by USA's and Russians for space applications. And in 1970s, it was also used for medical applications. In 1980s, it was used for industrial and engineering applications. And after that, during 1990s, there are like massive and huge amount of research and developments that are going on. And after that, we never heard of nuclear batteries and all the nuclear generators or atomic batteries. Like there's a reason why. I'll tell you after some time. So during 2018, so this university in Russia developed a nuclear battery, and like after the current like in the current nuclear technologies, there are current developments happening in nuclear technologies. And after 2020 and after in 2022 also, so current nuclear technologies are being developed. So this is the prototype of the nuclear battery developed by the Moscow Institute of Physics and Technology. Okay, now nuclear. So atomic or nuclear energy is like generated inside a reactor. So the heat inside the reactor is generated by tiny bullets like neutrons. So when a neutron strikes atomic nucleus, it splits into two, releasing splits into two, like releasing immense amounts of radiation and heat. So additionally, like other neutrons hit other nuclei, and it builds up a chain reaction. So it generates tremendous amounts of radiation and heat out of a small amount of nuclear fuel. So the most practically used nuclear fuel is uranium. We all know that uranium is mostly used as a nuclear fuel for nuclear reactors and nuclear power stations. And this radioactivity is the biggest danger for the environment because radiation is a long-lasting effect which is unstoppable. And to slow down the radiation or radioactivity, we have to slow down the reaction, like which will slow down the energy generation and finally will stop the radiation. So that's how we have to slow radiation and like radioactivity of the nuclear process. So now the radiation is the emission of alpha, beta, and gamma particles. So three particles are there, like alpha, beta, and gamma particles. So these three particles constitute the radiation emission. Okay. Now alpha particles are the combination of protons and neutrons. Okay, so alpha particles are the combination of protons and neutrons. You can see, yeah. So okay. So alpha particles are the a combination of protons and neutrons, and beta particles are the electrons or positrons, and gamma particles are the photons, which is the most harmful radioactive emission. So if gamma rays like directed towards a human or an animal or something, so like they will they will affect the animal or the human or that thing. So unlike a normal nuclear reactor, a nuclear battery is a device which uses energy from the decay of the radioisotope. So we are using a radioisotope that is the fuel for the nuclear reactions or the nuclear generation of energy, and we use the decay of that or the byproduct of that fuel. So it's not harmful. Okay, so the lifespan of the nuclear battery is like for decades, like and it's 200 times more efficient than the presently available lithium batteries or nickel cadmium or like other type of batteries available in the market. Okay, so now we have to know like what is radioactivity before we move on. So radioactivity is the emission of ionizing radiation from nuclear decay. Okay, now what happens? So this is a radioactive element or a radioactive atom, and it emits certain particles. So it emits basically three particles. So alpha, beta, and gamma particles. And there is a radiation going on simultaneously at the same time. So when the particles are emitted from the radioactive atom, so it generates energy. Now this is known as radioactive decay. Now, so radioactive decay or radioactivity is the emission of ionizing radiation from nuclear decay. So we have three types of radioactive decay. So first is the alpha decay, where alpha particle is released and from the same atom or from the same radioactive atom, a daughter nuclei is also released. For a beta decay, a beta particle is reduced and or produced, and at the same time, a daughter nuclei is also released from the radioactive atom. And for the gamma decay, it doesn't release any kind of particle; it releases rays. So in a gamma decay, gamma rays are released, and at the same time, a daughter nuclei is also released. Now, how does a nuclear battery works, or what is the working mechanism? So the nuclear battery or the reactor both works on the principle of chain reaction of nuclear materials, which ultimately leads to the emission of radioactive particles. So in a nuclear reactor, there are nuclear fuels which acts as a source of energy. So the reactor reacts on the principle of chain reaction of nuclear materials. Okay. Now, uranium. So uranium is the most practically used nuclear fuel worldwide. So we already know that, and we have talked about that also. And the reactor uses moderating materials like cadmium or boron which are also called moderators. So these moderators, what it does, these moderators actually control the reaction process. Okay. Now, if I use a cadmium or a boron moderator, so that moderator will basically control the reaction process or the speed of the reaction. So I can increase or decrease the speed using the moderators. Now, what they basically do is like they actually increase or decrease the chain reaction inside the reactor chamber. So inside the reactor chamber, there are reflecting materials available, materials beryllium, which are they are known as reflectors. So what this reflector does, like when the chain reaction is going on all the particles are released. So these particles reflect on the reflectors, or like for the here I am taking example of a beryllium. So they'll reflect on the beryllium reflector, and they'll hit back again. Okay, so like this, so like that, it keeps on going again and again. So this is like a cycle. So this cycle keeps on repeating, and like it goes on and on. So like that, the chain reaction happens, and the reactivity continues. So that's how a basic nuclear generator or a nuclear power plant works. Okay. So now the nuclear battery, on the other hand, uses emitted radioactive particles. Now, when the radioactive particles, when they are emitted, so a nuclear battery uses that particles. They don't use a chamber, something like that. They don't have reflectors or something like that. They use the emitted radioactive particles. These radioactive particles fall on a generating device, and they generate the electricity. So that's why nuclear battery is much smaller as compared to the nuclear reactors that we see in our day-to-day life. And the nuclear battery mainly uses the emitted alpha or the beta particles to produce energy. Like we don't use gamma particles here or the gamma rays here, because it's like too dangerous and it's harmful also. So like inside a nuclear battery, the alpha and the beta particles hit the electrodes at the end of the battery, and these electrodes create a potential difference, and which in turn produce the electricity to run the loads. So here we can see a diagram of a tritium nuclear battery, and I think someone has raised a hand.
No,
Is
sir,
there
you
any
can
question?
continue, sir.
Okay. Like if there are questions, like you can have the questions and you can ask me at the end of the session. Okay. So this is the schematic diagram of a tritium nuclear battery. So these are the tritium cells, the tritium elements or the tritium fuel cylinders, and these are the beta cells used. So these tritium cells emits radiation, and this hits on these photovoltaic cells, and these photovoltaic cells, uh, on the other hand, converts the radiation or the heat from the radiation into electricity, and it runs the system or the load. Okay. So we get to know that the nuclear, the atom battery use conversion methods to produce electricity. So it converts heat or radiation into electricity. So like nuclear materials are byproducts from the nuclear reaction, or spent nuclear fuels, or like nuclear waste can be used as a source of energy in a nuclear battery, because they are cheaper to get. They are like easier to easily like they are easily available, and like we can have them whenever we want to have them. Okay. And so these materials are tightly sealed in a chamber with the insulators and all other materials, and the energy generating device is connected to the chamber. Okay, or that container, wherever we have placed that steel or the material, and they produce electricity, or they convert the energy into electricity. So now these nuclear batteries can run for almost half a century. So this is like 50 years. So like a single battery can run for 50 years. Whereas a lithium battery that we use in our day-to-day life, or like in our phones or laptops or other things, they hardly last for like 2 to 3 years. After that, they start degrading, or they start losing their capacity. So we have to keep on charging the devices like 2 to 3 times a day. But in case of a nuclear battery, like if it started, it will go on like delivering the same amount of power for almost like 50 years. Like whatever the life is for that element, particular element, it will deliver. Like in general, it's almost like 50 years it can deliver power. So yeah. Now, why do we need like a nuclear battery? So now the question may arise like, why do we need nuclear battery? So like in a nuclear power plant, the nuclear reactor generates a lot of nuclear waste. Okay. So and the spent nuclear fuels and byproducts as a result of the energy generation and the nuclear fission. So these needs to be handled very carefully because these are like really harmful and radioactive in nature. And like if it gets in contact with anything outside the plant, it may harm the environment or like wherever is like in contact with that material. Okay. So as a result, like we can use the same material. We can take the desired materials out from the waste fuels or the spent fuels, and we can use them for in a nuclear battery. So like it's like if we compare like with a chemical battery, so the nuclear batteries are characterized by like they have high volumetric energy density and yeah, and they have high volumetric energy density, and like they can endure harsh conditions. Like they can survive harsh conditions also. Unlike other batteries, like which are like too delicate or they are like too fragile in harsh conditions, nuclear batteries can survive harsh conditions. That's why nuclear batteries or nuclear generators are used for space programs. So that's why NASA uses nuclear generators in the rovers or in the uh, robots they send to other planets like Mars or Moon or whatever. So basically, they use because it can survive the space environment or it can survive the harsh environments on other planets and other areas environments. So and also it's portable in size. Like if we have to deliver the same amount of power, we will need a large other battery. Like if we are using lithium battery, then we will need a large battery for the same purpose or for the same application. Furthermore, like an essential ingredient of the nuclear batteries is the waste. I have already told it's the waste from the nuclear power plant. So, like it depends. It depends on the nuclear power plant. Basically, if I am to manufacture a nuclear battery, if I have to manufacture a nuclear battery, I have to depend on the nuclear power plants near me. So, like when the fuel gets finished, or when the fuel is spent in the nuclear plant, then I can get those spent nuclear fuels and I can use them for a nuclear battery. Okay. So like new technologies like allow like us to make more smaller, safer, and more efficient and longer lasting nuclear batteries. And like they yeah, and like when the then it also reduces the cost of manufacturing the batteries because we don't have to actually rely on raw materials. We can get those materials from a nuclear power plant. And the cost also decreases, and yeah, like nuclear batteries can power like wireless devices, so they can mainly power wireless devices so that you can go on and on and on. And like nuclear reactors, when the general nuclear reactor and nuclear power plant generates electricity, and they but here in a nuclear battery they don't like use the chain reaction unlike a nuclear reactor. Okay, so the nuclear battery has no moving parts, so it's very compact. Like we can have a nuclear battery that's the size of a phone, and we can keep it in our pocket, and we can travel. So we can carry. It's like a portable power bank. You can use that thing. Okay. And it's like killing two birds with a single stone. Like we are not degrading the environment, we are using the waste to create a new thing. And at the same time, we are like decreasing the size of the huge reactors to small, compact, portable power form. And we can use it for future technologies and like for future research and development process. So yeah, like right now it's not available anywhere. Like it's only available for certain applications. But yeah, I think in a couple of years it will be available in it will be available just like any other type of battery in stores or any kind of general store. It will be available. Okay. This is an example of a nuclear generator. So it's the nuclear generator from the Nuclear Energy Commission, Canada. So it's a 2400 kilowatt thermal nuclear generator. So it's a thermal nuclear generator. Now it uses a low enriched uranium. That's a U-235 fuel, which is 35 kgs in weight, and it runs on a temperature of 550 degrees Celsius. Okay, so it's a thermal generator, and it can run for a period of 15 years. So once started, it can run continuously for a period of 15 years. So like there is no stopping or something like that. And apart from that, the fuel temperature can or the peak fuel temperature can go up to a temperature of 600 degrees if it's running on its full power. And yes, since it's a thermal generator, there are certain heat losses. So that's around 30 kilowatts of thermal heat loss. And like if the fuels are like exposed to the radiation when they are like having the reactivity or the radiation is going on inside the reactor or the nuclear generator, so they can have an estimated they can go to estimated temperature of 600 degrees Celsius with a continuous running of 100 hours. After that, like we have to decrease the temperature, and then again we can run it for another 100 hours. So this is an experimental value, like it can increase or decrease, and the Carnot efficiency is around 54%. Whereas if we convert it to electricity, conversion efficiency is 25%. It's for a thermal generator, so thermal nuclear generator. Okay, so yeah, now we have another generator, that is the electric generator. So it's the same nuclear generator, but it is the 600 kilowatt of the nuclear generator, electric generator. So what it has is like just like unlike a thermal nuclear generator, which has a shielding, and inside we have a reactor core, and inside the reactor core, the nuclear reactions are going on, and it has these vaporizers. So when the water is passed through this, it generates heat and it turns it into a steam. So the steam is converted and it runs the turbine and it generates electricity. So this is like a thermal power plant. So we are using it like it's just like a normal thermal power plant or a normal nuclear power plant. But in case of electric nuclear generator, so what happens is it's also using the same thing, but it's running a alternator in place of a turbine or something. So the turbine runs the alternator, and it can again regenerate the same heat again and again, and it runs in a cycle. Okay, so it runs in a cycle and it can generate the same amount of energy and heat and power from the same system. Like it needs 600 kilowatts and it will need 240 kilowatts for the same amount of power delivery. Okay, now these are some like market things like these are the amount of base load. If you are taking a base load 95% capacity for if you are running it for 15 to 20 years, so then this is the core life. And this is like so these are the diesel fuel costs. Okay, so this for per kilowatt hour, and yeah, like it so the nuclear fuel or the cost of the nuclear fuel, it actually decreases the cost. So yeah, now we have certain conversion methods. So, as I already told, like the nuclear battery runs some conversion methods. So the heat is converted into electricity. So, like there are two ways to convert the decaying radiation to useful electrical energy. So, the first one is the thermal conversion. So in this conversion, the output power is a function of the temperature difference. So it means that we use the high temperature or the radiation of the temperature from the radiation of the material and turn that into electricity. So and we have another conversion method, that is the non-thermal. So in non-thermal, the output power is not a function of the temperature difference. It doesn't depend on the temperature. Okay. Now Okay, so thermal conversion has three types of thermal conversions are available, three or four types of. So the first one is the thermionic converter. So in a thermionic converter, so the nuclear fuel is sandwiched between two thermal plates. So there are two thermal plates available, and these two thermal plates, in between them, there is a nuclear fuel available. Okay, so which creates and when the radiation starts, when the radiation decay starts or the radioactive decay starts, it generates heat, and those and that generated heat creates a temperature difference, which in turn converts the heat into electricity. So basically, thermocouples are used as converters or the plates for this thing, and it converts the heat into electricity. And the next one is thermoisotopic thermoelectric generator. So these are the generators that are basically used in many of the applications. They are used by NASA and other space agencies for their rockets and other space vehicles and launch vehicles or rovers, etc. So they are mainly used because they are like more reliable than the thermionic converters. So what a RTG or the radioactive thermoelectric generator does is like the nuclear fuel is basically capsule. So here we can see that the nuclear fuel is actually capsuled in a there is a capsule inside which the nuclear fuel is contained, and it's surrounded by thermocouples. So the heat trans or heat converting materials or thermocouples are actually surrounding the fuel. So when the heat is generated, so it directly converts the heat into electricity. So there is no need of any kind of sandwiching or any kind of plate is there. So there are as in terms of building or in terms of materials, so they are more reliable and they are more they are more finished quality products. Okay. Now we have the thermophotovoltaic cell. So I've already talked about that. So the tritium or whatever cell we are using or whatever fuel we are using, it's sandwiched between these two photovoltaic plates or the cells. And when the heat is generated, it converts the heat and when directed towards the photovoltaic cell into electricity. Okay, and we have another. So this is the Stirling radioisotopic generator or SRG. So SRGs are almost like they resemble the RTGs. So they are most like RTGs, but yeah, there is a slight difference. So here what happens like the SRG is a generator, or we can call it as a generator, and which runs on the Stirling engine. Okay, so we know the Stirling engine was like introduced way back, and it used like steam power and all of that in car. Okay, so what happens like it's there is a heater, and the hot end of the Stirling converter reaches when the hot end of the Stirling converter actually reaches high temperature. So the heat, so there is helium inside the inside that heater. So when it heats the helium, it drives the piston basically. So that piston helps it run the generator or the motor, and as a result, electricity is generated. So it's almost similar to that thing, but yeah, it's more like a generator type. So the piston is actually moving, so it rotates the alternator of the generator and it generates the power. So now these are the main kind of nuclear batteries. So they are non-thermal conversion type of nuclear batteries. So these non-thermal conversions. So the first one is alpha uh, alpha voltaic cells. So yeah, an alpha voltaic cell, it includes at least one layer of semiconductor material, maybe a PN junction or a NP junction, or a PNP or NPN or whatever there is. So it absorbs and converts the layer on the semiconductor layer and the alpha particle emitter. So whenever the alpha particles are emitted or on the semiconductor layer, it basically absorbs them and converts them into electricity. So suppose alpha particles from the alpha particle emitter are emitted towards the PN junction, suppose, of the semiconductor material, then it will absorb and convert the layer into a portion of energy, and it will direct that energy into that through those electrodes, and it will create a potential difference, and it will yeah, it will like direct the energy into the loads of the system. So it will create electricity. Now we have beta voltaic cells. So what beta voltaic cell actually does, here we can see that there are two electrodes available. So one is A or suppose B. So alpha beta particles are, emitted or bombarded at the same time. So when the radiation happens, or when the radioactive materials are radiating energy or alpha beta particles, so when it moves between the plates, it creates a potential difference, and as a result, the potential difference actually runs the whole system or the load. So like it's basic, simple, creating a potential difference using the radioactivity, and then in result, it runs the load. So and now we have direct charging generators. So direct charging generators, they consist of capacitor charge. So they mainly consist of a capacitor which is charged. Okay. Now the current basically, all the charged particles from the radioactive layer are deposited on one of the electrodes, and it basically charges the capacitor, and then the electricity is generated. So what happens, so we can see that there are a couple of capacitors, and all of these available, this rounded figure. So all the capacitors available. So whenever we just bombard, or the radioactivity is happening, or the radioactive decay is happening, it just the electrons or the particles just charge the capacitors, and in turn it will charge the, or it will deliver the power desired. Now we have optoelectric generators. So they are interesting generators. So because here a beta emitter simulates an excimer mixture. So what happens, we are using a light source, suppose an LED. So we are directing towards the DMD micro display. So then it displays it using microscope or powerful something like that, which can deliver the focus the intensity of the power, and then it focuses on this these plates, or where there is the uh, isotopic material available. So what happens, now the advantage of this design is that the electrode assemblies are not needed, and most of the beta particle can escape the finely divided bulk material, and contribute to the battery's net or the required power. So yeah, now we have another type of conversion methods which use reciprocating electromechanical batteries. Now, what happens is electromechanical atomic batteries use the buildup of charge between two plates, and it pulls the thing. So there is the radioactive material available beneath this plate, and this is it can be a copper chip or a conductive material. So whenever the radioactivity is happening, so it will pull this material downwards. So once this material is pulled downwards, so it will build up charge here, and whenever it's released, so it will release the immense amount of energy at the same time. So again, it will pull that plate, and again it will be released. So like this goes on, and it continuously delivers power for the requirement. So these are the types of conversions. So we have thermal conversions, and we have non-thermal conversions, and these are the type of thermal and non-thermal conversion methods, and the batteries or generators that we use. So yeah, now coming to the voltage, current, and efficiency of a nuclear generator. So, nuclear batteries basically use the radioisotope decaying process to produce energy for our needs. And the lifetime of a normal nuclear battery is around 10 to 20 years. So that's for a normal nuclear battery. But it also depends on the fuel or the material that we are using. So sometimes it can go up to 50 years, to 100 to 400, 500, or like thousands of years. Like it depends on the material and the life it has. So, like during the process, the battery gives out its maximum output. Okay, so it will deliver the same constant output throughout its lifetime, and it's not like that after a certain period of time it will like stop delivering the output until we have low power, we have low output. So it's not like that. It will deliver the same amount of power for years and years. And yeah, the output of the battery like depends on the fuel and the construction of the battery also. So like if we use a nickel 63 as a fuel source, so it increases the battery power output. So the PIN configuration structure, that's that basically the diamond battery. So I think most of we have heard about the nuclear diamond battery. So diamond is used as a nuclear fuel. So here, the PIN configuration structure or the diamond semiconductor boosts the voltage and increases the power output. So, like for a normal nuclear battery, the average open circuit voltage and the short circuit currents are like 1.02 volts and 1.27 microamperes, respectively. So, the maximum output power like of 0.93 microwatts can be obtained at 0.92 volts. Okay, so this power output corresponds to a specific power of about 3,300 milliwatt hours per gram, and which is 10 times more than a commercial chemical cells. Okay, so it's 10 times more or like more than, it can also be more than 10 times powerful than a commercial chemical cell. So for basic atomic batteries, the efficiency is around like 0.1 to 5%. And for high efficiency beta voltaic cells, the efficiency is around 6 to 8%. Okay. Now, for if there is a ionic pneumatic atomic battery, the efficiency can reach up to 33% also. And atomic batteries which uses magnetohydrodynamics, the efficiency can also reach to 90%. Like it depends on what type of material or what type of fuel we are using for the battery, what is the structure of the battery, or what type of battery it is. So the fuel can or the efficiency can range from 0.1% to 90% also. Okay. Since most of the research and development is going on as of still now, so we can expect to get around more than 100% efficiency within a couple of years or within a decade. So yeah, it will like surpass the current battery technologies, and it will have more efficiency and more power delivery than the current battery technologies. Now, yeah, I have talked about the nuclear battery that uses nickel 63, which delivers like 300 not a program of power. So yeah, it's developed by Moscow Institute of Physics and Technology along with like the Technology Institute of Super Hard and Noble Carbon Materials and National Institute of Science and Technology. So both of these three institutes developed this nuclear battery. So yeah, we have another actually battery, that's the nuclear diamond battery. So that battery actually has it uses uh, two metallic contact plates, and in between we have a radiation source, that is the diamond. We have a normal diamond and we have a insulating diamond available. So there are three types of diamonds. First is the radiating diamond, then we have a normal diamond, and we have an insulating diamond. And both of three are sandwiched between two metallic contact plates, and it delivers the power. So it's like similar to solar cells, and alpha and beta particles. Here, alpha and beta particles knock off the electrons to drive the current. So it uses carbon isotope. So for diamond, it's C14, but it starts decaying back from C14 to C12. So that is like for C14, it will have 8 neutrons and 6 protons. And for C12, it will have 6 neutrons and 6 protons. So it goes back from C14 to C13 and then to C12. So like that, the decay happens and then it generates the power. Okay. Now these are the carbon isotopes for the diamond, and here how it's actually made is like we if we see in a nuclear reactor, so we have moderators that we use. So whenever a nuclear reactor or nuclear power plant is decommissioned or like it's shut down, so we have those moderators available. So we can take those graphite or those control rods or those moderators, and we can take those radioactive graphite materials or those control rods or the moderators, and we can use them. So what happens now if we take those materials and we pass them through sublimation process, that's like the solid to gas process. So then we get a material or a product, and that output material is passed through a chemical process so as to get a sheet of radioactive diamond. Now, from graphite, we reach to a radioactive diamond through certain processes, chemical processes and other processes, and that radioactive diamond basically acts like a semiconductor. Okay. Uh, okay. So yeah. Now the radioisotope. So radioisotope is basically like the fuels that we use for a for a nuclear reaction. So we have atoms which has a nucleus, which gives in excess energy, it releases alpha, beta, and gamma particles, which goes through radioactive decay, and in turn it gives radiation. So radioisotopes are the radioactive isotopes of an element, we can call that, and they can be defined as atoms that contain an unstable combination of neutrons and protons. So the radioisotope is an atom that has an excess nuclear energy, which makes it unstable, and it releases alpha, beta, and gamma particles. And during this process, radioactive decay happens, and the radiation starts. So some of the radioisotopes can be used, which are used as nuclear fuel, are like radium-226. So we have tritium, we have tantalum 180M, then we have technetium 99, we have nickel 63, we have plutonium 238, we have strontium 90, we have promethium 147. We use curium 242 and curium 244 also. So these are the radioisotopes that can be used as fuel. So yeah, and this is a radioisotope tritium. So you can see that it's covered in a glass capsule, and inside the capsule we have phosphor coating. So these are the reflective materials, or we can see we can say them as the materials which hold the tritium radioactivity inside this capsule. Now, what we have to consider when you look for nuclear fuels, or like for the materials which will generate the nuclear power in a nuclear battery. So, for choosing the right nuclear fuel for use is a must, and we should also consider the correct fuel before using in the nuclear battery. So, we should avoid the gamma emissions in the chain decay. So, they are really harmful radiations for living beings and the environment. And gamma radiation passes through any material and needs a high lead shielding. Okay, so lead is used as a shielding material for gamma radiation, and at the same time it needs a high lead shielding also to stop it. So which makes it like the nuclear battery real heavy. So we can't use gamma. So we can't use radioisotopes which release gamma radiations. And yeah, half life of the nuclear material must be taken care of. So like it decides the number of years the battery will run without the need to replace it. So nuclear fuel nuclear fuel having a half life of around 100 years is like feasible to use. Like if you're using 10 or 20 years of half life for a material, like we have to change the material again after 10 or 20 years, or we have to dispose the material and get a new battery, which will be again viable for 10 years. So it's like best to use a material or a isotope which has a life of around like 50 to 100 years. So 100 years is like the best that we choose. Uh, like earlier we used uranium 238 for nuclear batteries, but it gives the radium 226. So radium 226 was released like as a byproduct during the decay of uranium 238, and so radium 226 again gives bismuth 214 as a byproduct. So which releases and during this process releases a large amount of gamma radiation. So which as a result, like uranium and radium are not used as they are not the most favorable radioisotope to be used. So they are not used as a result. Plutonium 238, on the other hand, is highly used as a fuel because it's more efficient, and because of its efficiency. So strontium 90 also releases gamma radiation, but like it does not require a lead chilling because the radiations are too weak. So the gamma radiations from strontium 90, like it's really weak, so it doesn't require a lead chilling. And another thing is that strontium 90 is not also available naturally. Okay, so uh, it's available naturally, but like it's rarely found. So the availability of nuclear fuel also, we have to also keep in mind the availability of the fuel that we're using. Suppose we are using strontium 90, then we have to consider that there is a large amount of availability of strontium 90, so that we can keep the battery running on forever, or like for the amount of years that we want the battery to run. So tantalum 180 is another fuel consideration. You can use tantalum 180 is a half life of 10 to 15 years. Okay, but the thing is that it's highly unstable at ground state, and it can decay within 8 hours. So as a result, like it's not feasible enough to use. But otherwise, it is a good source of fuel. It has that efficiency, but its half life is too short and it decays too quickly. So then the efficiency drops down after some time. But it delivers high amount of it has high amount of power. So yeah, these are the like fuel considerations that we must keep in mind like before choosing a nuclear fuel. And this is a experiment that we can actually do by if you want to do. So like due to the limited amount of radioactivity that can be handled safely in a house or in a home, like our nuclear device must be necessarily be weaker than the professional devices out in the market or in the industries. So yeah, we cannot expect a high amount of energy, or vast amounts of energy, but yeah, we can like experiment using this. So this was first experimented by City Labs in the year 2005, and we can use this. So what happens here is we have a radioactive tritium source, and it emits the electrons or the energy from the tritium source. So we have a NP type of beta voltaic cell. So all the electrons or all the energies are like bombarded directed towards the N type of silicon, and it converts the energy into electricity, and it runs the load here. So this is a direct conversion atomic battery. Now, in place of indirect conversion atomic battery, we can use the same tritium source, but what happens? Like we have to use the phosphor. So the phosphor actually converts the electrons into energy, and that energy is again converted to electricity. So yeah, so there is a you can say there is a middleman in between. So phosphor acts as a middleman, and it converts those electrons and those radiations from the source to energy, and then this energy is or the heat energy is converted to electricity. So it's like a photovoltaic cell, much like a photovoltaic cell. Okay. Now, if we are using it as a one-sided, so the voltage that we will get is like around 1.932 volts, and the current will be around zero point 0.1 microamperes for this one-sided. So this is the basic model circuit for the solar cell, and yeah, if you're using a monocrystalline solar cell or a monocrystalline photovoltaic cell, which has a size of 450 millimeters square, and we can use the amorphous solar cell, which should be have a size of 1,092 millimeters square. So the scale factor will be around 2.4. So these are the circuit diagrams for the solar cell or the photovoltaic cell. And yeah, like this is the current versus voltage for the amorphous silicon cell that should be used for the that could be used for the nuclear battery. And this is the current versus voltage for the monocrystalline solar cell. And this is the power versus voltage for the monocrystalline solar cell. So yeah, we can see these current and voltage figures for this amorphous silicon cell, and we can compare it with the current versus voltage for the monocrystalline as well as for the power versus voltage for monocrystalline solar cells. And yeah, so these are the battery power testing results. So we can compare the battery configurations, and uh, they show all the results. So these are the things for different types of solar cells. Their dimensions, they have different dimensions. They have different reflecting coating, and they have different sizes and all of that. They have different peak powers. They have different power figures according to their shapes and sizes. So the we can like actually choose. We can have all the results, and we can actually choose from these power figures and have a look like what type of battery is more feasible to be used. So these are the power versus light intensity. This is the power versus light intensity graph. So the green one is for a perfect nuclear cell. So the red one is the one which uses amorphous solar photovoltaic cell, and the blue one is for a monocrystalline solar cell. Now, this is the current and power versus voltage output of the graph for amorphous silicon solar cell. So, now this is for a double-sided solar cell. Earlier, we have seen the graphs for single or one-sided solar cell. This is for a double-sided solar cell. So, these are the current and or current versus voltage for a beta voltage cell. But this is for a theoretically perfect beta voltage cell. So you can see that the graphs are more constant, or the power figures are like all the current figures, and all of them are like more well distributed. But here we can see like they have certain anomalies and all of that. And, this is for the current versus voltage graph for professional nuclear battery, or we can say like the ones we can actually make in our home to actually experiment or in our labs. So we will have these figures. So for the perfect beta voltage, we'll have around 1.23 microwatts, and like 0.84 microwatts for the perfect one, and for the uh, ones that we will be making, we'll get around 1.23 megawatts. So yeah, now this is for the decay of the tritium. So we are using tritium. So this is the decay of the tritium over time and over years. So yeah, it's set for around 50 years, and like the graph goes for 45 years. So like 45 years of time, like the amount of tritium and like the tritium remaining and the light output it will deliver, it shows this. Okay, now this is another experiment that we can do. So if we have smoke alarms, or if we can like actually take any kind of smoke alarm, so we can actually see that the smoke alarm has uh, a type of material inside it. So This is for an so the previous one. So this one's for this was for like a beta voltaic and photovoltaic, and this one is for alpha voltaic experiment. So the smoke alarm should be a ionization type smoke alarm. So inside that we'll get certain material. Suppose we are taking americium. So americium has atomic number of 95 and atomic weight of 243. Okay, so it has a half life of 432 years. Okay, so for this experiment, we'll be taking the americium 241, which has a half life of 232 years. Sorry, 432 years, and we'll be using a 2N3055 transistor, which is the NPN configuration. So, when we are using the transistor, we connect that transistor to a load or an output, and we just remove the collector plate from the transistor, and in normal conditions we'll see that a semiconductor is inside that transistor. So the semiconductor or that silicon or that thing, so whenever in normal conditions it will deliver around 0.256 of 0.256 volts of power, but whenever it covered the that collector plate or that metal, so that no light is like delivered to the transistor. So in that condition, it will deliver minus 98 millivolts of power. Okay. So if we focus or if we throw light at the transistor, then it will deliver around 0.372 volts. But now in case two, like we are taking the same normal condition when there is nothing attached to the transistor. It just has a load, and in that condition, the transistor will deliver power of 0.262 volts, and in a covered condition, it will deliver around minus 100 millivolts. And like when this americium metal is like focused or directed towards the transistor, so the radiation or the radioactive decay is going through, and the bombarded radioactive particles are thrown towards the transistor. In that condition, it will deliver around 133 millivolts. So from 98 or 100 millivolts to it will deliver around 133 millivolts. So that's a huge difference. So from covered conditions or like during light conditions also it delivers like 0.372 volts. But if we use radiations, yeah, we can have like 133 millivolts of power delivery from that. So like this is an experiment like which we can do. Like, but I would suggest that this is just an experiment, and like we shouldn't do these experiments by our own, because like it can be like harmful also. Okay, so this is just an experiment. This is just to like have a look at the power figures, have a look at the efficiencies and all of that. Like this is not for anyone to like play around and do these things. Okay, so yeah, this is all the thing, and now coming to the applications part, like uh, nuclear batteries, like they are mainly used in wide range of applications, and like because they don't have to be maintained, they don't have to be serviced. We don't have to service them. They can withstand extreme environmental conditions, and they can withstand harsh environmental conditions. So they are used in a lot of applications. So we can use them for microelectronics. We can use them in sensors. We can use them for small devices, or for mobile devices, or for medical technologies, homeland security, automobiles, underwater technologies, defense, military technologies, industrial or engineering technologies, and space technologies, etc. So yeah, here is an example of like earlier. Uh, we used to have actually nuclear powered pacemakers available. Right now, the pacemakers that we see in the market, they actually use they actually use lithium ion batteries. But yeah, earlier, when the pacemakers first developed, they actually used radioisotopes or nuclear fuels. So yeah, because at that time, they actually had that technological advanced things, and that research was going on. So they actually created a radioisotope powered cardiac pacemaker. So yeah, we can see it uses plutonium 238, but yeah, it has gamma radiations. But yeah, they right now we know that, but yeah, at that point of time, they didn't knew that plutonium 238 is harmful to use. So they had used actually plutonium 238 in a pacemaker. Like it had a lifetime of 10 years. But yeah, right now, there are pacemakers available which has a lifetime of around for 80 to 85 years. So that's a huge number. Like a pacemaker has a lifetime, or it has a life of around 80 to 85 years. That's a huge number. And if we use lithium-ion batteries in place of a nuclear battery in a pacemaker, so that lithium-ion battery will have hardly a lifetime of 10 to 5 or 10 years, and within that 5 or 10 years, you have to again replace the battery. So yeah, that's and the batteries are really costly. So it's not cheap also. So the lithium power batteries are the pacemakers are not cheap. Okay, so now coming to the advantages and disadvantages of nuclear batteries. First, I'll tell the advantages. So the nuclear batteries they have long lifespan for around decades, and they are more reliable sources, constant power supply. And nuclear batteries need no maintenance because there are no moving parts involved, unlike other type of machines or generators. And it delivers high intensity of power. Okay. And nuclear batteries are they are very small, portable, compact, and lightweight. And yeah, nuclear batteries give out little, or they actually give out little or no waste at all, because they actually use the waste. They don't release any type of waste. So, if a nuclear battery is dead, we can dispose the battery. There are certain disposable techniques or methods to dispose the battery, and that nuclear battery can be again used in another in the manufacturing of another nuclear battery. So there is a cycle that goes on, and yeah. Apart from that, there are certain advantages also. So right now, the initial cost of production of a nuclear battery is really high, and it's not commercially available in the market also. Like they are mainly used for industry and other applications. So right now they are not available for we public. Okay, so for us, and it's still in the experimental and development phase. And the energy conversion techniques, uh, they are not advanced right now. So yeah, there are certain techniques which are still being developed, but the current conversion techniques, like the thermionic conversion techniques or the non-thermionic conversion techniques or the direct and non indirect conversion techniques, they are not feasible enough to give out the desired efficiency from the battery. So new conversion techniques are being developed so that so that they can deliver more power from a lithium or any type of other chemical batteries. And yeah, radioisotope sources that the used in the nuclear batteries, they are not available like uh, in huge quantity as of now. So yeah, kind of a chain market is being developed so that the power plants actually supply those used nuclear fuels to the nuclear battery manufacturers, so that they can actually develop nuclear batteries from the waste, and then they produce a new nuclear battery. So yeah, and uh, like for conclusion, I like to say that nuclear batteries, the see nuclear batteries are around from 1900s till date, and since there are many fixes and developments and innovations and technological advancements happened, and as technology grows, uh, the need for more power and heat will undoubtedly grow along with it. And the principal concern of nuclear batteries is that it involves the use of radioactive materials. So, people are really concerned about that, like what radioactive materials will have effect on us or on the environment. But there are scientific experimentations and conclusions that that state that there is no leakage of any kind of any radioactivity or radiation from the nuclear batteries, because they are sealed or contained tightly in such a way that there is no leakage, or there can't be any leakage. And yeah, the process of the nuclear battery to the final disposal, and again to manufacture nuclear battery, it has to go through certain protection standards, and so that is known as the radiation protection standard. So it has to meet some of the radiation protection standards. And yeah, I can clearly see that the future is a long-lasting battery, and it lies in nuclear batteries and technologies related to this nuclear battery. So it has a lot of potential for future uses, and with further research and experiments, nuclear batteries can be made safe enough to be used everywhere. And with the displacements of electrodes, and we can reduce the prices of initial production, and we can have cheap and usable nuclear batteries which could be used in our day-to-day life, and which could be used by us, like we people. So yeah, that's it for this topic, and thank you for listening to me patiently.